The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Okay, next we have Dr. Chris Motter from Washington State University.
So today I'm going to present about some work that I had done before I got to Washington State when I was a postdoc down in New Zealand working with Ken Elwood. So just like to acknowledge some of my co-authors here. Aaron and James were undergraduate students who carried out a lot of this experimental study, and so just wanted to acknowledge their contribution. So motivation for this research was the Canterbury earthquakes in New Zealand. The significant financial losses that occurred in those earthquakes, the time that the Central Business District was closed after the earthquake, and all of the assessment that went on afterwards to decide if structures needed to be repaired or could be occupied in their current state, and things of that nature. And in that process, there were a number of buildings that were demolished that had low, what we're calling damage ratios. So the dollar amount needed to carry out the repair versus the dollar amount needed to replace the building. And some of that had to do with the structure of insurance in New Zealand at that time. But based on kind of these numbers and stats that you see here, it was very clear that there was more guidance that's needed on the assessment of residual capacity and repair. And so the focus of this particular talk is going to be on structural walls. And so you see here some damage, examples of damage that had occurred in the earthquake to structural walls and different types of failure modes showing through there. Crushing failures, bar buckling failures. On the next slide here, there's an example of a out-of-plane buckling failure of the wall. Some of these walls, as you can see there, were pretty well detailed. So these aren't necessarily older walls with deficient detailing. Some of these are more modern designs where we're seeing fairly heavy damage in the structural walls. And so we posed the question, can these be repaired? Should these be repaired? And we've certainly seen examples where they are being repaired. And there's just a couple examples that I'm showing here. Coming out of Chile after the Mal earthquake. And you can see that the walls are being propped up, jacked and braced, and so that work can be done on replacing damaged concrete and restoring damaged reinforcement. So in our study, again, we are focusing on walls and we're looking at heavy repair. Ken is going to present a little bit later on repair methods for moderate damage, but this is really focused on repair to severe damage. So this is cases where we need to replace concrete, we need to replace reinforcement. And so we started this off by doing some tensile testing of reinforced or welds in rebar. And so you can see the test matrix here that we used, and we had some straight bar tests in there just for a control. And we were looking at a couple different weld cases. We were looking at a double lap splice weld where the bars just overlap. We're looking at a butt splice weld where two bars come together and there's little splice bars along there that provide the connection. And then we looked also at mechanical couplers as a way to make that rebar connection. And all of this was coming right out of the New Zealand standard on these welded connections. So this is just showing examples again of the splice welds. So the double lap splice weld and the butt splice weld, and then the coupler down there, and our just rebar testing apparatus. And the lap splice welds, not surprising, due to the eccentricity in those welds, they create some bending moment on the bar itself, right at the connection there, and so those fractured early. They fractured at the connection earlier than the fracture would have occurred in the rebar. And so you can see examples of the fracture that occurred for the indirect butt splice welds and the coupler, and the fractures occurring in the bar itself. So we didn't have failure at the connection in those cases. So here's a plot showing the strain in the bar when the fracture occurred. And again, the double lap splice welds are not up to New Zealand standard. They had fracture before the strain had reached the elongation limit in the standard. So based on this, we were either going to go forward with the coupler or with the indirect butt splice, and we decided to move forward and use the indirect butt splice in our wall repairs. The coupler we decided was kind of bulky and a little bit hard to implement, so we went with this approach. So I'm going to show now the test specimens. There were 2 test specimens in this program, and these were just old tests, leftover test specimens from completed tests that we had done as part of a previous study that was looking at minimum reinforcement requirements in walls. And so these walls were lightly reinforced. They meet the minimum requirements in New Zealand, which are pretty similar to the minimum requirements in the United States. I should point out those units are SI units rather than US units. But the walls had, they did have boundary elements at the end, as you can see there, but generally very lightly reinforced. So this is a look at the load deformation response from the original 2 tests. And so we're calling these M5 and M6, and I'll kind of refer to that call out as we go along. M5 was a wall that was tested under a standard cyclic protocol. M6 was a wall that was tested under an earthquake record. So a nonlinear time history analysis was run to come up with the response of the wall in a particular ground motion, and then that response was used to test the wall. Okay, so the first one was tested essentially to a state of failure, whereas M6 was actually not tested to a state of failure. Okay, so we had very different levels of damage at the end of the test. So you can see on the left there, M5, we have more damage in the boundary elements, crushing that's extending into the web. And for M6, we had kind of modest, more modest damage at the boundary elements and a lot of cracking through the wall. So given the difference in the level of damage to the 2 walls, we made a decision that we were going to explore different repair techniques, different levels of repair for both of these walls. So for M5, and the designation that I'm going to adapt now is the R indicates repaired wall. Okay, so M5 is the original wall, M5R will indicate the repaired wall. So for the repair of M5, we decided that we were going to replace all of the concrete and all of the reinforcement essentially over the plastic hinge length. Okay, so the whole bottom region of the wall there, we're going to replace all of the concrete and reinforcement. For M6R, we decided that we were just going to replace reinforcement and concrete at the boundary elements. We weren't going to do replacement in the web, so crack injection in the web. So just showing kind of schematically what that looks like. For M5R, we're replacing the full plastic hinge, and then for M6R, just replacing at the boundary elements and doing crack injection in the middle portion of the wall. So I wanted to go through the repair procedures that were used here. So this was M5R, and we cheated a little bit for the repair. In an actual building, the walls would still have gravity loads on them. You would need to prop and brace the walls like I had shown on that earlier slide. But not very practical to simulate in the lab. So we took this outside and went to work on repairing it. And it started off with hydro-demolition of concrete. So this was a pretty cool procedure to watch. It's a water jet at high pressure that essentially blasts away all of the concrete and leaves you just with reinforcement. So the first step was hydro demo of all the concrete down in the plastic hinge. Then we cut out all of the rebar and kind of aligned everything back together. And then we reinstated the reinforcement. So this is where we were using the indirect butt splice welds to put in the new longitudinal reinforcement and also providing new transverse reinforcement as well. And this is what it all looked like when the new reinforcement was all tied up and ready to go. and then we built formwork around the repaired region and used repair mortar to complete the repair. So we didn't actually pour concrete into the specimen. We're using a repair mortar here, and we poured it right through. You can see that little opening there at the top. So we poured right through there. And of course, there would have been formwork on this. I'm showing a photo without it, but poured it right in that opening there to complete the repair. For M6R, this was the one where we just repaired the boundary elements. So we used just jackhammers to break away all of the concrete here, expose the steel, and then we followed the same process as for M5R. We replaced all of the reinforcement at the boundary element here and used the indirect butt splice welds again to reinstate all of the rebar in that damaged region. And also prepared it for crack injection, which is kind of what you see there over the cracks. And so, and then again, poured repair mortar in through an opening to complete this repair procedure. So moving along into how we actually tested these things, these were tested as cantilever walls, so aspect ratio of 2. And the lateral actuator is providing the deformation demand at the top of the wall. The 2 vertical actuators were used to apply axial load to the wall. Okay, so they weren't actually applying overturning moment in this case. They were just applying axial load to the wall, and this was tested as a cantilever with aspect ratio of 2. And there's a photo of what the test setup looked like in our lab. You can see the repaired wall there with the nice shiny repaired region down at the bottom, and we had some out-of-plane restraint on the loading beam to make sure that everything was tested in plane. Okay, so it's just an in-plane test that we're doing on the wall. And instrumentation shown here. It wasn't a particularly heavily instrumented test, but we had enough sensors to get the sources of deformation. So we could get the deformation from shear, the deformation from flexure, sliding down at the base, and break down those components of deformation. Testing protocol, we used a standard cyclic testing protocol for both tests. Okay, so if you remember, one of the original tests had been an earthquake protocol, but when we did the repaired test, we used a standard cyclic protocol. So most of my comparisons are going to compare to the original test that had the standard cyclic protocol. So getting now into the test results. Just wanted to quickly go through the progression of damage that we saw in the test. So this is just one example. This is M5R. And there's the load deformation response in the upper left-hand corner there. And we got out to about 1.5% drift, and this was the state of damage at that point. So certainly it was, cracking as we would expect, but we didn't see spalling at that phase of the test. And then as we got out to 2% drift, we got some spalling of cover concrete, and that was where we first had buckling of reinforcement. Same thing in the negative loading direction. We picked up our first bar buckling at 2%, spalling and bar buckling, and it progressed from there. As the cycles continued at 2%, the buckling became more severe, and we started to get some little bit of out-of-plane movement of that wall. As we continued along, loading out to 2.5%, we fractured reinforcement, and that's when we started to really get a significant drop in strength, as you would expect. We continued along and we were loading out to 3.5%. That was the original protocol. And as we got out to about 3% drift, we got an axial failure, crushing failure of this wall. So that was just an example of one of the tests, the type of damage that was observed. But this table here is showing a comparison of the first observation of each of these damage states. So the first cycle at which we observed spalling, buckling, and fracture. And without getting too much into the details, the main point here is that there was, the 3 tests were fairly consistent. So the damage states were occurring at fairly consistent points in the test, suggesting that the damage pattern for the repaired walls was matching that of the original walls. And again, this is just showing what it looked like at the completion of the test. M5R actually had an axial failure. M6R did not reach an axial failure. We got through the cycles at 3.5% without having an axial failure. And so this is showing the load deformation response of the repaired specimen M5R on top of the load deformation response of the original specimen M5. And so you can see that we had a good match between the repaired specimen and the original wall out to about 2% drift, at which point we had a little bit faster strength degradation in the repaired wall than we did in the original wall. And this is showing the other repaired wall, M6R, the load deformation response, again on top of the load deformation response of the original wall. And this one matched a bit better. So this was the repaired specimen where axial failure did not actually occur. And in the positive direction, we have a very good match on the hysteretic response. In the negative direction, we got out to 2%, and then a little bit faster strength degradation from there. So these are the two repaired tests on top of one another, just showing that, that difference in behavior after about 2% drift. Backbone curves. The main thing that I wanted to point out here is that although the backbone curves are pretty similar, again out to 2% drift, there was a difference in the initial stiffness. And so that's shown in the tabulated values at the bottom right there. The stiffness of the repaired specimens decreased by about 33% to 50%, so kind of 1/3 to 1/2 decrease in stiffness of the repaired specimens relative to the original tests. So I'll get to that a little bit more. Dissipated energy, this is just showing that the area within the hysteretic loops, very similar, out to 2% again, and then at which point the repaired specimens degraded a little bit faster. This is the components of deformation for measured during each test. And again, we see similar values between the repaired specimens, which are shown at the top, and the original specimen, which is shown at the bottom left. So similar trends in the data. Most of the deformation is coming from flexure. Flexure is contributing on the order of 80% of the deformation. But if we break that down a little further, that's the plot at the bottom right here. And what we actually see, this is showing the percent of that flexural rotation that's coming from the unrepaired portion of the wall versus the repaired portion of the wall. And what we're seeing in that plot is that the unrepaired portion of the wall is giving us more deformation than we had in the original test. Okay, so we've lost essentially some stiffness in the unrepaired portion of the wall. And so the plot on the bottom left is the stiffness versus drift, and you can see that the repaired specimens are less stiff than the original specimen. And again, if we break that down into the stiffness measured in the repaired region versus the stiffness measured in the upper portion of the wall, which is the unrepaired region, we have a match between the repaired specimen and the original specimen in the repaired region. So we were able to restore the stiffness in the repaired region. But in the upper region, where we didn't do any repairs, we've actually lost some stiffness, which you're seeing in that plot. To conclude, the performance of the repaired specimens similar to the original specimens out to about 2% drift, at which point the strength degradation for the repaired specimens was more rapid than for the original specimen. And the approaches that we used worked well in this particular instance. The indirect butt splices, we didn't have any weld failures that were observed in the tests. When we had bar fractures, they weren't actually at the welds. And the strategy that we had used to decide on the level of repair also worked out. We didn't see any issues with damage at the joint between the repaired region and the unrepaired region. And so again, flexural deformation accounted for about 80% of the total deformation. And if we broke that out a little bit further, we did lose some stiffness in the unrepaired region. Okay, so we lost about 50% stiffness in the unrepaired region. So coming back to the original question, is it feasible to restore the performance when we go through these types of heavy repairs? Based on our study, the short answer would be yes. Of course, we only did 2 tests, so I don't want to extrapolate too far beyond the results of what we've done. But it was a case where we were certainly able to restore the performance of the specimens. So with that, I will conclude and acknowledge all of the groups in New Zealand that helped us carry out this research. Quake Corps provided funding. The other organizations that you see here either provided materials, labor, or consulting on the project. So with that, I'll conclude and take any questions that you guys have.